Let's get started, please. A couple of announcements to begin today. Lab 4 has been posted, so Lab 4 is on the website. We're going to talk about Lab 4 in just a little bit. Before we do, I wanted to give you kind of an overview of what's going to happen between now and the end, since we're getting kind of close to the end of the semester. We've got just a few weeks left. So Lab 4 has been posted. It's due next week. There is going to be at least one more, well, exactly one more lab after Lab 4, so Lab 5 will be posted probably next week, and we do probably on the last day of class. So that's coming up. I really wanted to try and get another homework in there as well, but we're just not going to have time, so here's what I'm going to do instead. I'm going to post a homework assignment. It's going to be entirely optional. You will not have to turn it in. You can do it if you want to. It'll be great practice for the exam, but you do not have to turn it in. It will not be graded. I don't think it's fair to throw a whole bunch of stuff at you like that at the very end. So 2 more labs and an optional homework assignment are coming up. And then the final exam, of course, the date for that is on the calendar. So you can actually kind of start to piece together what your grade in the course might be based off of how you've done so far and how you expect to do on the remaining stuff, right? Everything that I have is on Blackboard right now. So please take a few minutes, check over the stuff on Blackboard. Mistakes happen. So, you know, if you see something that looks like it was entered incorrectly, please shoot me an email so that I can fix it sooner rather than later. It's always good. If your grade looks really wrong or if it's a 0 and I don't have it marked in there, it might mean that I didn't get it for some reason. But I can't know unless you reach out to me. We can try to figure out what happened. Yeah, question?
Yeah, so if we do the optional homework, is that like just purely for like personal like gain or like we're gonna submit that for
I was not going to accept it as something that you could submit for a grade. I was just going to have it be purely optional. I'll still post the answer key like I do for all the other homework assignments, so you can check your work and make sure you're on the right path. But I was not planning to grade it at all whatsoever. I guess I could reconsider that notion and think if it might be worthwhile to do so. But you know, my TAs are students too, and so I don't know that asking them to grade 3 assignments at the end of the semester is particularly a kind thing to do to them either. So we'll see. I'll think about it. We'll see. Any other questions? Yeah.
Lab 3, we talked about that.
The grades have been posted to Blackboard. I actually have the Lab 3. I don't have them on me right now, but I do have those. So if you want to swing by and pick them up sometime, I'll be in my office. I'll put this on the website too. I'll be in my office next Monday and Tuesday, so you can swing by Monday, Tuesday next week, or drop me an email if those days don't work. If you want to come in sooner, drop me an email and I can try and meet you Thursday or Friday this week, but I'm pretty busy. So. Yeah, the grades are up there. They were excellent. They were really good. Pretty much the only reason people got marked off was if they forgot to turn in one of the pieces. That was the biggest reason why people lost points. It was a lot of hundreds. So, any other questions? Any other questions about what's coming up from now to the end of the semester? So, let's talk about Lab 4 a little bit then. Hopefully you've already had a chance to go over the write-up. If not, I'll give you kind of the quick high-level overview of what I want you to do. I want you to implement a stack. So I realize that maybe not everybody in here has taken 241 yet. That's okay. You don't need to have the data structures class under your belt to be able to understand what's going on here. It's a pretty simple data structure. So a stack. It's named aptly. Think of like a stack of plates at a cafeteria, right? If I take something off, I remove it from the top. If I put something back on, I put it on the top, right? So everything is coming from the top of the stack. And that's true here as well. So this is a very simple stack. We can only push 1s or 0s onto this stack. We can't push anything else. It's actually possible to make a stack that lets you push letters, for example. Or larger binary values, but we're going to keep it simple. We're going to keep it simple and just stick with a pure binary stack, 1s and 0s. The operations are labeled push and pop. So push means I'm going to add something to the stack. Pop means I'm going to remove something from the stack. It's always going to occur from the top. So I know this is going left to right, not top to bottom, but in this diagram, top is here. Top is on the right-hand side. So when I add stuff to the stack, when I push stuff onto the stack, it gets added to the right-hand side. So I pushed a 1, then I pushed, a 0, then another 0, then a 1, then a 0. When I pop stuff off, it comes off the same point, the right-hand side of the stack, right? It comes off at the same point. This is called a last in, first out scenario. So the last thing that I put onto the stack is going to be the first thing that I take off. So that's how a stack works. Let's see. I'm trying to remember if there's anything strange. I'm asking you to create a circuit for this for the data path portion only. We're going to talk about data paths today. That's the topic of today's class. The data path is only part of the circuit. It's not the complete circuit. If you want to make the complete circuit, knock yourself out. It'd be great practice because we're working our way in that direction. You're going to see stuff like that on the exam, for example, so it'd be great practice. But the only thing you're required to do is the data path. All I want to see is the data path. We'll talk more about data paths in just a little bit, so I'm not going to spend a whole lot of time talking about that right now. One other thing to be aware of for this lab that's a little bit different from what we've seen in the past. These values here are empty, right? So my stack has a defined size. In this case, I think I said 16 bits. So there's a defined size. That size never changes. It can hold 16 things tops. But maybe it only has 5 things in it, and the remaining 9 slots are empty. So to represent those empty bits, I really, really want you to use X, which stands for I don't care what this value is. It doesn't matter to me. That's a lot different than using like 0, say, to represent an empty space. But it's not that bad. You can actually assign X to a signal just like you assign 0 to a signal. Okay? It's the same mechanism as assigning a 0 or a 1 to a signal. Just assign it an X instead. So for truly blank spaces, these should be X's. In fact, I'm kind of wishing that I put X's in there to represent that, but I didn't. The lab write-up does explain that piece as well, so if you have any questions about that, please let me know. That's the one thing that's a little strange, I think, about this lab. It's not really strange, we just haven't seen it before. It's pretty straightforward. And then just like in previous labs, you are responsible for hooking things up to the buttons and the screens, so that's your task. That is your responsibility for this lab. I'm giving you even more control over this than last time. I basically gave you a bare bones top file and say, have fun, knock yourself out. So you're going to have to figure out how to hook that up to the buttons. You're going to use at least 3 buttons, reset, push, and pop. Right? Those are our 3 operations. So I want reset, push, and pop. The outputs need to be hooked up to the LEDs. The outputs in this case are going to be whether the stack is empty, whether it's full, and what the top value of the stack currently is, what the topmost value is currently on the stack. And then the stack contents itself are going to go on the LCD screen so we can actually see the entire stack all at once. So as we add more values to it, we should see them all scoot over and that new value appear on the screen. Let's see. The rest of it's pretty straightforward. Similar to other labs, you have to, of course, create a test bench and annotate your simulation, just like I've asked you to do on all the labs this semester. You have to create a high-level state machine. That should be the first thing that you do, right? Have lots of practice doing that. Are there any questions right now about this? Yes? It will actually show a blank. It will not show an X. It will show a blank space. I think I did say on the lab write-up that if you really have problems with the X's, you can use 0s, but I would really, really like it if you use X's. At least give it a shot before you switch over to that. It should work. I've updated the LCD code to work with X's and put blanks in that spot instead. So it should work. Any other questions about this lab assignment? Of course, you're free to work with partners like always. Please let me know if you do have questions about this, either on Piazza or shoot me an email, go to TA office hours, et cetera, et cetera. All right. let's move on to our topic then. So the topic for this class today is data path. So before we get to this review question, let's take a step backwards and talk about what the heck a data path is. What is it? What is a data path? Why are we talking about data paths? What is it? What's it for? Yeah.
It's basically a certain piece for data operations.
Exactly. So we've been constructing high-level state machines, which incorporate some additional pieces of information that have not been in our finite state machines of the past. Namely, we can do arithmetic now, right? We can do comparisons. We can store variables. Those are all new things to our high-level state machines. And we need a way of controlling all that stuff. Our variables are all going to be stored in registers. If I'm doing comparisons, I need to have those components hooked up. All of that stuff goes into what we're calling the data path. So we've really got two distinct pieces of our circuits when we're talking about high-level state machines. I've got the state machine itself, right? The circuit for the state machine itself. That's actually what we're going to talk about on Thursday, so that's coming up. That's Thursday's class. And then we've got the data path, which is the variables, right? And also inputs and outputs. But we have to be a little bit careful when we say inputs and outputs. Some of those might be inputs and outputs to our state machine, not necessarily overall inputs and outputs, global inputs and outputs, right? So sometimes we need to provide information back to the state machine so that it can do its job. So what am I going to expect to find in data paths? What is that? Is that a bomb? I hope not. Yeah. Registers, right? So for all of our variables, we need registers to store them, right? So those are going to be in the data path. What else are we going to find in our data path? What other kinds of components? See some up here, right? We have multiplexers. Why do we need multiplexers for? Primarily, yeah. Right. So if I need to update the value of a variable, I need to choose what that next value is going to be. Maybe I want to read it in as an input. Maybe I want to provide some kind of operation, arithmetic operation on a variable and use that instead. So multiplexers are going to be used for that purpose. What's controlling this? This is the select bit to our multiplexer. What's controlling that? Yeah. It's the finite state machine, right? So we're going to see finite state machines on Thursday. Our outputs of our finite state machines are actually going to be control signals for the data path. Right? That is a large part of what this is. So these signals are actually going back to the finite state machine. These are not inputs per se. They're coming from the finite state machine. Cool. And so we've also got arithmetic. We've got an adder operation. And we also have a comparator. Comparisons. We've talked about those in previous courses, right? Those are all components, potential components of our data path. Are there any questions about what a data path is, what a data path isn't, what a data path cannot do? Cool. So let's talk about this question then. This is the data path for the pulse counter. I covered this in the video that hopefully you watched before today. So we talked about the pulse counter a lot. We talked about it a lot last week. It just counts pulses from our input stream. This is the data path for that high-level state. This is what that data path looks like. I made this using the Zybook data path builder. I forget what section that's in, 5 point or something like that, 5.6, something like that. There were some limitations that I was not fond of. For example, I couldn't rename these. That really bugged me. I don't know why I want to rename my inputs. Such a basic thing to do. But the structure is correct, right? This is my input N. It says A, but it's actually N. If you look at the high-level state machine. This is my output. We would call that event, I guess. That's what it is on the high-level state machine. And then these are control signals that are coming in from the finite state machine. You want to choose how to load this variable and whether or not to load the variable. So the first question is this, right? An alternative form of the pulse counter is what I'm calling the continuous pulse counter. It's one that after I count, if n is 3 and I count 3 pulses, I want it to go back to 3 and count over again, right? So I just want it to continuously count. The original version didn't do that. The original version, as soon as our counter got to 0, we were done, basically, right? We're done after that. So the first question is, how does this data path change for the continuous one, the one that's just going to go back and start over again? Go back and start over again. How does that change? Hopefully you have the high-level state machine for that example that we did last week. That'll help you a lot in answering this question. And then the other one, how does this change for the paired pulse counter, where we're counting pairs of pulses, not just a single pulse at a time? Take a few minutes, go back, take a look at those high-level state machines from last time, from last week. If you weren't here last week, find somebody who was. Hopefully they took good notes. And we will talk about the answer to this in a few minutes. You're knee-deep in certain
Oh. Or, yeah. Yeah. So you have to review that. Yeah. Sorry, there's lowercase a.
I know, I see that.
That's not part of the data path, that's part of the. Yeah, there's some.
Okay, let's talk about these problems. So for this one, right, it's kind of tricky because we are leaving the finite state machine alone. The finite state machine changes, right? We're going to talk about what that circuit looks like on Thursday. That's not our concern today. So the question is, you know, when the finite state machine changes, how does that change this stuff? How does that change what's going on here? So let's talk about the continuous pulse counter, the one that we want to reset after we count n pulses. We want the counter to go back to n and continue counting. Do we need any extra components? Do we need any extra signals? Somebody help me out with that one? What do we think? What do we think? Do we need anything extra? I mean, yeah, go ahead. That's what this guy's doing, checking to see if count is equal to 0. Count is represented by the register, and we're feeding it into a comparator with 0. So that's what this guy's doing. So we have that piece. Yeah. Do we need another register? What would that register represent? The previous value. So do we want to store the value of n? That's a good question, right? Because how do we reset our counter back to n if we don't know what n is? Or do we just read it from the input again? I don't remember actually how we did it. Is it just hanging out on the table? Yeah, is it just hanging out up here the whole time? How did we do it in our finite state machine? Did we read it from the input? I think we just read it from the input, right? If we just read it in from the input. Which means actually that this value could change potentially too, right? It could actually be something different if we wanted it to. Yeah. Do we need another mux? Okay.
So
what would that mux do? Where would we see it?
it would be between A or N. Between N and the mux is F.
Okay.
I'll pick between, I guess, the current value of N and 0.
The current value of n and 0.
Use
So these are all great suggestions. I think actually though we don't need any modifications at all. I don't think we actually need any modifications at all. Which, yeah, that is the FSM controlling those signals A and B to the data path, so we could, just put for A could just, well, these reset count back to N, you could just put the correct selector in there. Exactly, that's exactly correct. So we have this signal coming from the finite state machine that's controlling the multiplexer, right? The finite state machine can trigger this value whenever it wants. It can do the same thing for this one too. It can trigger this value whenever it wants. So if we want to change the behavior, and the finite state machine wants to trigger this at a different time, or additional times, or fewer times, or whatever we want, right? This signal is still here. That doesn't mean this has to change. It just means that the finite state machine is going to be controlling it a little bit different. Right? So the data path itself is going to remain the same. And if you really want to justify it, think about this. We don't need any extra variables, right? So the fact that we're using the same variables as before is a strong indication that we just need this one register, right? We don't need any additional registers. We don't have any other options for loading this variable. The only thing that's going to go in this variable is n or count minus 1. We still have those. That's the same as it was before, right? That's the same thing as it was before. And in terms of the output, we still only care whether or not the counter is 0. That's the only thing that we care about. So if the possible values for the register are the same, there's no additional variables needed to accomplish the task, then don't mess with it. Don't mess with something that works. We can just change how we control this data path, and it can still behave, give us a different behavior. Right? The finite state machine controls the behavior of this circuit. This is simply controlling how the data flows based on whatever behavior the finite state machine gives to us. Does that make sense? It's really kind of a separation of elements of our circuit. One for the data, storage and manipulation of data, and the other part, the finite state machines we're going to talk about on Thursday, is the behavioral part. Is that clear, everybody? So we don't need to make any changes. What about the second one? So for the paired pulse counter, we actually talked, I think, about 3 different possible changes for it. Anybody remember what those 3 different ways were that we could go? Yeah.
You add 2 more states. You use a variable to track whether or not you're on your first or second peak, or you double n.
Right. So those were the 3 options. Let's talk about each one. If I double n, how does that change the data path? If I double n, yeah.
You just have to add some kind of multiplier or something that's just going to make whatever your A is.
Sure. Exactly. So we haven't talked about multipliers yet. You could use multipliers, a multiplier, or you can take an adder and just put n into it, both sides. That gives you 2n. That would work. So we just need an additional component to multiply this by 2 if we're going to take that approach. What if we want to take the variable approach? What if we want to track and see what was the variable for? Was it to track if you're on your first or your second, right? So how many bits was that variable? Just one. 0 if I'm on my first, 1 if I'm on my second one, right? So what does that mean then in terms of the data path? What do I need to add in here? The new variable. Where are variables kept? They're kept in registers. Or in this case, since it's a single bit, it's just a flip-flop, right? Just a single flip-flop that we need. So, or a load register is fine, right? That's fine. Right, so I would need, if I'm going to use a variable to solve the paired pulse problem, I'm going to need an additional register, I need an additional place to store that variable, and I'm also going to need additional control signals for that register, right? I'm going to need to control when that value is loaded, when that value changes. I think just the register itself would be sufficient. I think the finite state machine could handle both the inputs and the load signal to that register. So we would just need basically another register just kind of floating, kind of hanging out by itself over here. Right. What about the third option? If we add additional states, what would we need to change if I add additional states? Yeah. Nothing. We could reuse it just as it is. Use it just as it is. If the solution to my problem is changing the state machine, the data path can stay the same. That's kind of the whole point of keeping the two separate. I can change one without necessarily having to change the other. If my solution to the problem is to add additional variables, that directly affects my data path, right? Directly affects my data path. If my solution to the problem is manipulating variables or inputs, in this case, or outputs, multiplying n by 2, that's going to affect the data path, right? So if I'm adding additional variables, if I'm performing additional arithmetic operations, the data path has to update to reflect that. If all I'm doing is changing the finite state machine, all the variables are the same, all the arithmetic operations are the same, the data path doesn't have to change. The data path can remain as is. Is that clear? Kind of relates back to our first problem too, right? We didn't change any storage, we didn't change any arithmetic, so the data path can just stay as is. Cool. All right. If there aren't any questions, let's move on. Yes. So last week we also talked about high-level state machines for the button debouncer and the knob, turning a knob on the FPGA. Actually, to kind of make this easier, does anybody have the high-level state machine for the debouncer that we did last week in their notes? I wouldn't mind putting that up on the board so that we all are working off the same one. So that we're all in the same place. And then I can do the knob one as well if somebody's got that available. You got it? Can I borrow it? Real quick? Bottom? Okay. Gotcha. Yes. So we've got two states. Change. Goes to 0. Plus, and then okay, let's review this. Thank you very much. Let's review this high-level state machine really quickly first. and then I'll turn you loose on constructing a data path for this example. So we're trying to debounce buttons. When I push a button down, it jitters, right? It doesn't make direct contact right away. So we need to give it a little bit of time to stabilize. The way that we did that was we looked at the signal. If it was high for a certain period of, not necessarily high, if it was high or low for a certain period of time that we called delta, right? Then we accepted that as our stabilized value, right? If it changed, then we reset our counter. So we start here. This is our start state. If we see that no change has occurred in our input, it was 0 last clock cycle, it's still 0 this time, or it was 1 last time and it's still 1 this time, I'm going to increase this counter, count plus plus, right? As soon as I detect that count is equal to delta, whatever delta is, right? Delta can be set to be anything. Then I'm going to take my input and propagate that to my output, whatever that input value is. It could be high or low, right? And then as long as it doesn't change, I'm just going to hang out here. As soon as that input value changes, I'm going to reset my counter and then go back and start the whole counting process over again, right? And if I detect a change when I haven't hit delta, then I'll also reset that whole thing. So how many variables do I have here? Yeah. Yeah, so change and no change is the same variable. Yes, absolutely right. What is change and no change? What is that going to look like? It's just a 1 or a 0. So another way to think about this is previous value, right? What's the previous value that I saw? Well, this is has the input changed? I'm not necessarily. This is more of asking a question rather than a variable name, I guess. Maybe that's a poor way of putting it. Has the input changed? Right, is what we're asking. Is what we're saying here. Is the input not changing? Is what we're saying here. So there's no variable name. These aren't variable names. These are just saying whether the input has changed or not. But you do need a variable in order to answer that question that tracks your previous value. So with that in mind, how many variables do we have up here? Yeah. At least 2. So we've got the one that's tracking the change, and then we've got counts. Any other ones? Where does delta come from? Is that a variable? Is that an input? I think it could be either. It's a constant, right? It's just a constant. So you can treat it as a constant in your data path, which is as simple as just drawing a box with delta in it. That's fine. Use that to represent delta. So 2. I think there are 2. Right? I think there are 2. Again, I don't care about the finite state machine circuit. That's Thursday. We're going to talk about that on Thursday. I care about the data path. So I know I've got 2 variables. Make sure those variables have a place to live in your data path. Think about how those variables are going to change. What are the operations that I'm performing on those variables? Comparisons, arithmetic, et cetera, right? Think about what those components need to be and incorporate those into your data path. Take a few minutes, talk to your neighbors, and we'll go through the answer in just a little bit. Okay, well, okay, that's right.
It's unfortunate that you can't stab because when I got my knife, I started to go out. This guy get it like 35%. Yeah, I got my knife.
Thank you. Okay, let's talk about this one. So first things first, I like to start with my variables. I like to give those variables a place to live. So much depends on those variables. If they don't have a home, there's not much we can do about that, right? So we decided we have two variables. Let's give those variables a place to live. Just some registers, just some load registers. So what were those? Count was one, right? And then the other one we called previous or something like that, something to that effect. These registers have a couple of inputs, so the data comes in the top usually, and then I've got this load signal, right? Also, just a very quick side note for the clock down here, for the clock signal. We're at the point in the class where you don't have to hook this up. It's usually implied, and it just makes your diagram more spaghetti-like to include the clock signal. So if you just leave the clock signal hanging empty like that, that's perfectly okay. I'm not going to mark you wrong for it. It's perfectly accepted shorthand to just leave the clock signal hanging like that. So we've got this load signal. What's going to be where is this load signal going to go? Yeah, question?
Yeah, so when I was doing something design, it said you don't have to deal with single bit inputs, and wouldn't previously be a single bit input?
Yeah, single bit input. So is this an input or so we need to remember it, right? So it's actually a variable because we have to remember it somehow. We could one way that you could vouch for getting rid of this is if we had additional states, right?
It's just that in the design it said that like the variable and inputs, I thought that didn't want to make
I'm just trying to think of how we would represent this without having some mechanism to store it. So how would we represent the previous value if we didn't have a place to remember what that previous value was? We could make additional states, right? That is one option. I could easily make states saying the previous value was a 1 and the previous value was a 0. It's only 2 extra states, and it would not make this much more complicated than it already is. That's perfectly acceptable, in which case you are absolutely right. We could get rid of that. It could go away entirely. If we don't want to do that, if we want to say, I like my state machine as is, and I want to use a variable to track this, I'm struggling to think of how we could represent this without having a place to put it.
Is it also like output?
Is it also output?
Is it also out?
Is it also out? No, it's not. It's not. It's a good question. It's not.
No,
I'm sorry?
we
We still need another register. That's a good question. We will answer that question, but I kind of want to build our way up to that particular part. We will get to it, I promise. Let me think about this as we're working through. Maybe I can come up with a solution that eliminates this flip-flop, this register from the solution. But right now I'm struggling to come up with one. So back to what we've got up here, right? What's going to be controlling those load signals to these registers? Where do those go? Yeah. These are from the finite state machine, so we don't have to worry about them. That's not our problem, right? That's not us. That's not something that we need to worry about right now. They're going to go to the FSM. So we should really maybe give them names, right? Potentially, right now I'll just mark them as FSM to indicate that they're being dealt with by the finite state machine. Clock is also not our problem. Clock's taken care of for us. So we're in pretty good shape. Now we just need to figure out what's going into these, right? What's going into these registers, and then do we need to do anything with the output of these registers? So let's start with count. Let's start with count. What are the possible things that could happen to count? Yeah? You either put in 0 or you increase it by 1. So we've got two choices. How do I make choices? What components do I need to make decisions? Yeah? We need a mux. We need a mux. So I'm going to stick a mux right here. Right? 0, 1. Doesn't really matter. So in one of these, we're going to have what? The value of 0. Right? That's one potential option. In the other one, we need count plus 1. So we need an adder. I'm running out of space already, and I just got started. One input to this adder is going to be count. The other input is going to be 1. And then I need a select bit. What's controlling the select bit? Where'd that select bit go? Finite state machine. Not our problem right now. That's our problem on Thursday, but not right now. Right? Finite state machine is going to control that. So we're good. Count is... The input of count, at least, is satisfied for now. We might need to do some other stuff with count a little bit later. Well, actually, let's talk about that now. What else is count used for? So the stuff that's going into count, that's when count is on the left-hand side, right, of an assignment expression. If we have any other arithmetic expressions that deal with count, that's going to be output. So do we need to do anything else with count? I see some people nodding. What else do we need to do with count? Yeah. We have to compare it to delta, so we need a comparator for that purpose. So I'll just put an equal sign for our comparator. Count is going in, right? Delta is also going in, whatever the value of delta is. Where is this output going? To the finite state machine, right? It's part of the finite state machine, so it's not our problem right now. And I think we're good with count, right? Am I missing anything with count? Is there anything else that count does that we haven't accounted for? Okay, so let's switch our focus to this guy, this previous value variable. How does this get updated, right? So what are the possible things that could happen to this? Yeah. Right, so it can be either 0 or 1 depending on whatever the previous value is. I could think of a couple ways we could potentially accomplish that, right? So, do I need a mux here to represent those two options? That's what we did last time, right? We used a multiplexer. Do I need a mux to make that happen? Yeah.
Could we just have a signal coming in from the FSM that goes straight into the register?
Exactly. We can just have this be coming in straight from the finite state machine. That's fine. Right? That's fine. So we store this value. Although, let me think about that for a second. So what are we going to do with the output of this value then? How's that going to be connected? How do we do? We need to detect whether this changes, right? So that's the other side of this. How do we detect whether it changes? What do we need to do? That's where things get a little tricky, I think. Yeah.
Well, will the FSM read its value and
So we need to do that. We need to detect whether it's changed or not. Yeah.
Comparator between previous and
Right. So between previous and I mean, this is really, when we say this is coming from the finite state machine, this is really in, right?
Yeah.
This is really in. So let's
That's
label it as such. In. So we need a comparison between whatever this is and the input. So we want to see if they're equal or not, right? So that could go there, and then this can also loop around and go here. This looks a little strange, right? Does this sit well with you? Is this okay? No? I see some people shaking their heads. Are we comparing it to itself? That's a good question.
not necessarily.
So this value is only going to get read in on the rising edge of the clock cycle. So and when load is high, right? So if we don't trip this load signal, then this value is just going to be ignored. But let's consider, let's say we do read in this value, right? We read it in. Whatever is here is going to then propagate to the output. And then we want to compare that to, this is changing in real time. This is changing asynchronously whenever it wants, right? Whenever it wants. Really? So we then need to compare what it was on the previous cycle, the output of their flip-flop, to what it is now, which is just a direct connection. I'm okay with this. I think this is okay. It looks a little strange. I can see why you would think that maybe we are comparing input to itself, but this is inserting a little bit of a delay. Right? The fact that we have this edge-triggered flip-flop means that we are storing the previous value of the inputs and comparing that against the current value of the input. Right? That's what's happening. Okay. And so then the output of this comparator goes where? To the finite state machine. Finite state machine. Yeah, so is there anything else that we need? Anything else that we need in our data file? Anything I'm missing? Yeah.
Well, in the side look that the outputs they also have registers.
For the outputs?
Yeah, because they said the value needs to be held between like rising edges of the clock, so they have the outputs also.
I think that's a valid concern. So the suggestion is that the output should potentially be stored in registers so that they don't change between rising edges of the clock. They're held stable during rising edges of the clock. That is a very good suggestion if we are dealing with a Moore machine, right? Because Moore machines, the outputs are related specifically to what state we are currently in, right? If the outputs are asynchronous, and if we're using a Mealy machine, then the inputs can directly affect the outputs all the time. Yeah.
If we're dealing with one machine, why would we need to have the outputs in a register in the first place? Because you're not going to change state outside of rising edges.
Yeah, that's true. You're not going to change state outside of rising edges of the clock. I know exactly what's. Let's see. So the Zybook says. I might actually just pull the Zybook up here in a minute and take a look at it and review exactly what it says. I actually typically skip that step myself. I usually don't stick my outputs into registers, especially for Mealy machines. I don't do that because Mealy machines, the output depends on what state we're in as well as the inputs, which means the output could change directly if this changes. It could change right away. I'm trying to think of a counterexample or a reason, the reasoning that the Zybook gave for that. I'll tell you what. While you're working on the next problem, I'm going to go read the Zybook. I'll get a better answer for you. Is there anything else we need to worry about in terms of this problem right now? Anything else? So we've got 1, 2, 3 inputs coming from our finite state machine. We've got 2 outputs going back to our finite state machine in order to help it do its job, right? I think we could actually set the output if we really wanted to. If count is equal to delta, and there's no change, that means the previous value is equal to the current value, then we want the inputs to be propagated to the output. We just want to send it through, right? Want to send it through. We have that information. We've got these 2 multiplexers. Right now we've got them going back to the finite state machine, but I think the data path could actually handle that. So I could have a multiplexer. Well, here's in, right? Or actually, this might answer the question that you just asked me about the output. We either want the, well, no, let me think about that. So if we store the output in a register, like you were suggesting, we could tie that to the input. And then the load signal could actually be connected to these 2 signals handed together. Do you see that? If they're both true, then load the new value for the output. You see kind of what I'm getting at? Let me sketch it out. Let me sketch it out. I think this is actually good. So I'm going to toss an AND gate down here, and then hook this up to the load signal. So what is this saying? If count is equal to delta, and the previous value is equal to the current input value, if those things are both true, then I want you to take whatever this input value is, load it into the register, and that now becomes our output. Isn't that what the finite state machine says? Isn't that exactly what the finite state machine says? Yeah.
Like if we were asking about that, can we expect it to do that?
So I think there's some wiggle room here. I'm not sure. The data path is dealing, so this does examine the values of these variables and the outputs over here. I see your point. What?
Wasn't that kind of the point being modular, not evaluating it, like having the
Yeah, you're absolutely correct. You're absolutely correct. I think you're right. That maybe this is getting maybe we're leaking into Thursday's topic a little bit. I think I actually agree with you. Thanks for challenging me on that one. Did you have a question?
Kind of similar, like when the finance is expecting certain values, with respect to like the each value of count, does not have a way to tell just the finance.
I'm sorry?
Like if you were to,
Well, we could still output, these signals
Right.
to the FSM. There's nothing stopping us from doing that. I think I agree with Elizabeth, though. I think maybe this piece is potentially should be relegated to the finite state machine side of things and not the data path. So I got a little bit ahead of myself there. Yeah. From the previous input? Yes. So I see what you're saying. There's a timing concern here, right? There's always timing concerns when we deal with registers. That's something that we've kind of been ignoring up until this point. But I'm glad you brought it up. There is a timing concern here. What if, in the time that it takes for these values to make it through the comparators and change this signal, this value changes to something else? Should we use this more stable value here? I think that's actually a pretty good suggestion, to use the more stable previous value instead of this asynchronous value. The only issue is that's not how our finite state machine is drawn up, but maybe you make the argument that the finite state machine needs to be altered then. I think that could be a substantial argument as well. So the answer is yes. I see your points. Timing analysis is a separate issue. We're actually going to talk about that a little bit on Thursday as well, the timing issues behind these things. Were there any other questions or comments about this at all? About this particular example? Let's see. If there weren't any questions about that, then I know there's only 15 minutes left. I really want to talk about this problem, so I want you to take some time and see if you can construct the data path for this guy. This is the knob interface that we also talked about last week. We may not have time to go through the whole solution today, but I'm going to try and go as far as we can in the 15 minutes that we have left. So take at least a few minutes to see if you can construct a data path for this high-level data sheet. Yeah, that's true. Well, I mean, we only got the one variable, right? And there's not a whole lot going on there. Or they Okay, let's actually talk about this one. It's actually not. I actually think it's perhaps less complicated than the previous example that we went through. So, how many variables do we have? What are our variables? Is A, B is actually not a variable. That's our inputs, right? I know it's been a few days since we looked at this example. A, B is an input. A, B is not a variable, it's an input. Previous is a variable, right? That's the previous value. So what's the rationale behind this? We're trying to test whether the knob's turning left or right, clockwise or counterclockwise, based on the order that these buttons are pressed in. Right? That's the logic behind this high-level state machine. So we need this variable previous. That's one variable. Do we have any other variables? Got outputs. A, B is an input. I think we just have one variable, just one. So it's not going to be all that bad. So here's our register previous. The load signal is going to be handled by the finite state machine. That's not our problem, right? That's true of all registers for storing variables. What happens to previous? What's the input? What's coming in? Just AB, just whatever this is. This is the only time previous actually gets set, is this transition right here. It gets set to be AB. What are we doing with the output of previous? Do we have any operations on it? Yeah.
You have to compare it to 1, 0.
So we've got some comparisons, two of them. So I'm going to need a couple of comparators here. Compare it to 1, 0 and 0, 1. Output. Where are these going? They're going back to our finite state machine. Not our issue. Right? Not our problem. And anything else? Yeah.
Would you need a variable for the clockwise? Because like when you're in the wait state, clockwise would just be its previous value, right?
Right. I'm glad you brought that up. So this actually relates back to the question you were talking to me about before, which is, do we need registers for our outputs? In this case, the answer is absolutely 100% yes, right? Because we see that clockwise is 1 here. Well, we never change it, so it's just going to need to retain its previous value here, right? I'm very glad you brought this up. Yes, we absolutely 100% do need a register to store clockwise, or a flip-flop to store clockwise. So we need this as part of our data path, absolutely, 100%. Again, what's going into this? What's the input? It's coming from the finite state machine, it's not our problem. What about the load signal? That's also the finite state machine, that's not our problem. The output, finite state machine, not really our problem, right? So it's just a register that's kind of floating. Yeah.
Why does this one need it?
So clockwise gets set in both of these states, either low or high, depending on which state we're in. When we come back to this state, it retains whatever its previous value was. So if I take this transition, clockwise is going to remain 1. If I take this transition, it's going to remain at 0. But I can't remember that value unless I have it stored in a register, in a flip-flop. Yes? I'm sorry? Tick does not. So well, let's talk about tick, actually. So does tick need one? I think is a better question. So we go to counter, we say tick is equal to 1, and then we immediately go back to the wait state right away. Do we need to store tick? One clock cycle, yeah. Who's in charge of tick? Finite state machine's in charge of tick. Tick is not our problem. We don't need to store tick. Tick is just going to be high. In fact, we could make an argument that clockwise, well, no, actually, no, we can't make an argument that clockwise could be handled by the finite state machine because it depends on the previous state that we came from, right? The finite state machine could not handle clockwise, could not do it in this case. It's not possible. So we actually have an example here of needing a register for the output and another output that clearly does not need a register. Yeah.
They don't contain like
Well, the other stuff that's going to happen is, you know, we haven't talked about the finite state machine side of things yet. That's happening Thursday.
Right, so like, could you just put this scenario, could you put clockwise on the finite state machine side of things? Or?
It wouldn't work, right? Because clockwise doesn't depend on entirely on what state we're in. It also depends on what state we came from. So we can't do that without the register. We can't do that.
No, like, could you put the register on that, but you can't do that?
Oh, well, technically it's part of the data path side. Any registers that are not storing what state we are in, so states are also stored in registers, those are part of the finite state machine. Any other registers we need, whether they are for variables or outputs, are part of the data path. Notice the data path does not have to be connected, right? There's nothing saying that all the pieces of the data path have to be hooked up to one another. I can have two floating pieces entirely separate. The finite state machine will connect those together eventually, right? I feel like there was one other question that I wanted to ask you, and then I forgot what it was. That's okay. Are there any questions for me about this stuff? We'll definitely get more practice doing this. Yeah, question.
I guess the previous is equal to 1, 0, and A, B is equal to 1, 1. How, if we had implemented that specific logic and the one below it for the other transition, how is that not really part of the data path?
That's kind of a gray area in my opinion. If you include it in the data path, I wouldn't necessarily count it wrong. If you include it in the finite state machine, I wouldn't necessarily count it wrong. Yeah, I think it's kind of a gray area in this case. All right, I will see you guys on Thursday.